Okay, so we have a fairly interesting question over here. It's question 8, and let's just read the question statement. So 8.1 says there are 3 identical light bulbs A, B, and C, which are all rated with 6 watts 12 V. So this is the 6 watts is the power, and then the 12 volts is the potential difference. 8.1.1 requires us to define the term power, and we all know that is the rate at which work is done. And then 8.1.2, we have to calculate the resistance of each bulb when used as rated. All right, so you will see just later in the video how is it that you actually do that. And then the question statement continues to say, okay, now the light bulbs are connected in a circuit with a battery with an EMF value of about 12 volts. So they've given us the EMF value, which is 12V. Remember the difference between EMF, internal potential difference, as well as external potential difference. So we've just spoken about that in the last lesson. And then also the battery has an internal resistance of R, and the value of it is 2 ohms. And then we have to refer to this diagram, the schematic that they've given us below, and then we have to assume that each light bulb is the same as that each light bulb, assume the resistance of each light bulb is the same as that calculated in the previous question. So here they asked us to calculate the resistance, and now continuing forward we have to assume that that resistance that we calculate is the value for each of these light bulbs over here. So let us just go through this schematic quickly. So this is the positive terminal of your battery, the negative terminal, and then conventional will be like all over through the light bulb A. Then this light bulb C and B are connected in parallel to each other. So just always now revise in your head those principles we've spoken about resistors in parallel as well as resistors in series. So you might be asking yourself, but you have a light bulb. So remember, a light bulb has a resistance in it, and that is the resistance that we're actually going to calculate in question 8.1.2, right? And then we have to now calculate the total current in the circuit. And then 8.1.4, the potential difference across light bulb C. So let's see which light bulb is that we have to calculate the potential difference here. So if we were to, for example, put a voltmeter here, what reading would we actually get? Okay, and then we have to explain why that light bulb that we just calculate the potential difference for will not burn at its maximum brightness. Continues to 8.2, where we have resistors A, B, and C, and D, which are all connected to a battery with an EMF and a negligible internal resistance. We are given the diagram below, and I love these questions because they are analysis questions. They require you to actually look at your schematic and understand it. And now the first question is asking us to give a reason why the current in resistor A is greater than the current in resistor C. So think about everything that you've learned about parallel as well as series resistors, and realize that this what do you call this thing, this resistor is connected in series, and then these two C as well as is connected in parallel to B and D, right? So think about it before you actually get to answering it. So resistor C is then removed. If you remove this resistor, how will the current in resistor B compare to the current in A? And then you have to provide a reason for your answer. So I hope you're able to take down that question, and then we're gonna just go on into into answering it. Okay, we are on lesson 30, which is it's just us doing an exam question on electric circuits. And as we've already read the question 8, so we were given 3 identical light bulbs. Remember, light bulbs have a resistance through them, and you will notice that these 2 light bulbs B and C are connected in parallel to each other, and this one is connected in series. Okay, so now question 8.1.1 wanted us to define the term power, and as we know that power is actually defined as the rate at which work is done. So that is a simple question. It's worth 2 marks. And then the question 8.1.2 wanted us to calculate the resistance of each bulb when used as rated. So these are the specifications that we're given. We are told that the power at ABC for all of these light bulbs is 6 watts, and then their potential difference is 12 watts, all of them, they are identical. So it's just a matter of selecting which a power equation you're going to use. Remember, these are available at the back of your question papers. The one that I'm going to use is this one that says P equals to V squared over R, so that I can actually find my R, because I'm given the power as well as the potential difference. So I'm just making this subject of the formula is going to be R equals to V squared divided by P. Putting this in the calculator. So the potential difference was 12 squared divided by 6 watts. And this, if you put it in a calculator, you're going to come to a value of about 24 ohms. So it's a straightforward question. They will mark you for the equation, the substitution, as well as the final answer. That's where those 3 marks are coming from. So now they saying to us, so let's say, so we found that the resistance is 24 ohms as well as 24 ohms here. So they're identical, these light bulbs. So now they're saying that light bulbs are connected in a circuit with a battery having an EMF of 12 V. So they've given us the EMF and an internal resistance of 2 ohms. We've already, these are given to us. And then what did they say? They say refer to the diagram below. So this is the diagram that they are referring to. And then say assume that the resistance of each light bulb is the same as calculated in question 8.1.2. So now they're saying the resistance is this value that we've calculated, which was 24 ohms. All right. And then they're saying that switch S is closed. So I'm just trying to move up my screen. So when they close that switch, they say calculate the total current in the circuit. So how do we go about doing that? Well, because I'm given the EMF as well as the internal resistance, and I can also find the total external resistance, I would say there are many ways to do this. I would go about using my equation of EMF, which says that R plus R. And if you don't know how I got here, please refer to the previous lesson that we did. So I know what the EMF is. I'm looking for the total current in the circuit. I can find what the total external resistance is. This is given to me. Okay, so now, meaning I'm looking for the current, meaning that current, so E would actually be over R, R plus R, all right? Or the EMF, let me stop saying E, and then we'll find the value of our current. So now, but let us first find R. How do we find R? So there are two things that we're noticing. We're noticing that to find the total resistance, we have to say, okay, the total resistance would be made up of, let's say, these two resistors that are connected in parallel, RP parallel plus RA. So we know what RA is 24, but let us find what RP is. So 1 over RP, to find it, we say 1 over RP equals to 1 over RB. Remember, these two are parallel, plus 1 over RC. So it's just 1 over 24 plus 1 over 24. So you find 1 over RP equals to 1 over, how much is that? So that is going to give us 2 over 24. If you put it in a calculator, you get to 1 over 12. So to find RP is just a matter of inverting it. So we have RP actually equals to 12 ohms. So now we go back to our equation. We substitute the value of RP, it's 12, plus the value of RA, which is, how much was that? 24. So 12 plus 24 is going to give us 36. So meaning the total external resistance is going to be 36 ohm. And then we can put it in our equation. So let me write that. So keep that value in mind, because I'm just going to wipe this whole thing now. So now to find R, we say E, we found it was given to us as 12. We found the total external resistance to be 36, if I'm not mistaken, if I remember correctly. Yes, 36. Let me see, 36 plus, and then internal resistance was 2, which is equals to I. And then you actually just a matter of putting this in your calculator, and you come to a value. So you find that I is actually equals to 0.32 ampere. So that is the total current in our circuit. So now the other question says explain why, which question am I? Calculate the total potential difference. So we've now calculated the total current, and now this question requires us to calculate the potential difference across light bulb C. So you have to calculate the potential difference. It's almost like putting a voltmeter here and finding the reading across that. So let me just wipe everything. So to answer this question, like I said, we have to now follow the direction of the current. So we know that this is the positive terminal and this will be the negative. So current will be flowing in this direction, right? So we'll have a total current IT coming, passing through this light bulb A, and then here somehow it will split. It will come to this. So this the total current will split into two, because these two are in parallel, so they are current dividers. But we can agree that IT will equals to the current at A, which will also be equal to the current that these two light bulbs will receive, which we call IP. So this is IP is for the two light bulbs together, not separate, right? And we already found out to be 0.32 amperes. So if we're looking for, so meaning that so we have that IP, that's fine. And now, because these two will kind of have the same, they will split this current, but the total current coming to them will still be the same as this one. I hope that is making sense. Okay, that wasn't in the short. So I said the total current that is coming through here will also be the total current that will measure at the light bulb A, which will also be the current for both these light bulbs together that are in parallel. We haven't split them together. And another important thing to note would then be that for resistors or light bulbs, because this, remember, these light bulbs have resistors, so it's almost like resistors that are in parallel. The current through them is the same. What does that mean? This means that VP, or the current, the potential difference for this parallel connection will be the same as the potential difference through B, as well as potential difference through C. So where am I going with this? So VP equals to VB, which equals to VC. So if we were to put a voltmeter here and a voltmeter here, they would all measure the same, the same potential difference. So now, but I can calculate VP using Ohm's law. So we can start from saying RP equals to VP over IP, right? So I'm looking for the resistance of that parallel connection which we have. We can find this, and we also are given this. We found it to be 0.32. So what are we looking for? So we can just say VP actually equals to RP multiplied by IP. So we have RP, we calculated it to be 12, if I'm not mistaken, multiplied by this value of 0.32 here, and then you find that to be 3.84 volts. But we were not told to calculate VP, we were told to calculate VC. But we know that because these are parallel, they are connected in parallel, the potential difference through them will be the same as the total potential difference for that parallel connection. So meaning VC, which actually equals to VP, which is equals to 3.84 volts. Hope you can follow my sense for trying to explain this entire thing. And now a very interesting question, this one, they saying to us, explain why light bulb C in the circuit will not burn at its maximum brightness. And that question is worth 3 marks. So look back, we've just calculated what the potential difference across VC is, and we found it to be so VC is equals to 3.84 volts. But let's look at our specification. What is our specification? It says that our specification was it's 6 watts as well as 12 volts. So what does that mean? So the power rating, the output voltage was 12 volts. And then for a given resistance, so remember, if we go back to our equation, we would say that for a given resistance, power is directly proportional. So we use, this is the thing we used. So power is directly proportional to the square of the potential difference. And then since the potential difference across this light bulb, C is less, so it's 3,84. It's less than the operating voltage, which is 12 volts. It means that this light bulb will actually not shine at its maximum. So the potential difference through this light bulb is actually less than what the specification said that the voltage could be on this light bulb. So that's why it will actually not shine at its maximum, meaning that the output at this will be less than what was specified. Okay, so now we're moving on to question 8.2. So I've just drawn a schematic diagram that they gave us in the question for question 8.2, and they saying that these resistors A, B, C, and D are connected to a battery having an EMF E and a negligible internal resistance as shown in the diagram. So these are analysis question. They saying to us, the first question, 8.2.1, give a reason why the current in resistor A is greater than in resistor C. Okay, so let us look at this. So we're saying that, so this would be the negative positive terminal as well as the negative terminal. Remember, the total current, if we were to, current was to move in this direction, they will have, it's an unconventional current, this one, so it's not conventional, that moves from A to, that moves from positive to negative. So if this total current was to move through here, the total current from the battery would actually move through a resistor A. But now look what would happen. It would come that IT, when it gets here, it would be split into two. This total current would be split into the current for this resistor, as well as now the current for these two resistors. Let's call them I, B, D. So the current coming here would actually be lesser than the total current. So this one, this resistance would have the total current flowing through it. Let's say that total current was 2. And then when it gets here, because these two are now in parallel to each other, because there's a branch here, as you can see, IC would definitely be less than the current through this resistor, would definitely be less than the total current that is supplied because of that splitting. So there's a, because they are in parallel, they are current dividers. So remember that resistors that are in parallel to each other are parallel dividers, so they would split the total current. I hope that is making sense. So now question 8.2.2 says we remove this, they remove this resistance here, and this is what we are left with. And they saying to us, let me see, how will the current in resistor B compare to the current in A? So look at this, still using unconventional current. Same current will come through A, there's the current IT through B, up until the same current. All of these resistors are connected in series, and we know that resistors in series have the same current as the total current. So IT will be equals to IC, which is no, IB, which is equals to ID, which is equals to IA. So the current would be the same through all of those resistors. I hope this made a little bit of sense. And then yeah, this brings us to the end of actually that question.